Hi, my name is Dmytro. I'm from Boston University. Today I will present to you Epsolute, efficiently querying databases while providing differential privacy. In this section, we will go over the outsourced database framework, the concept of differential privacy, and ORM. We'll need these blocks in our solution. Clouds become a dominant form of data warehousing, and with that come requirements on security and efficiency. In this work, we concentrate on defenses against access pattern and communication volume attacks, which actually imply at least protecting the data at rest. Relevant existing solutions fall into one of three categories: the ones which protect perfectly against snapshot adversary, but do not account for access pattern or communication volume attacks. Some other solutions rely on enclaves, usually SGX, but it has some limitations. On top of very little memory and extra hardware dependency, the SGX itself is a subject to access pattern leakage. Some solutions target access pattern or communication volume leakage, but usually only one of them. Shrink wrap targets both, but uses linear scan and full padding. And so we present Epsolute, most practical and secure mechanism in the outsourced database model that protects both access pattern communication volume using differential privacy and does not rely on SGX, linear scan, or full padding. Let's get started with the framework. We define the following components in the outsourced database model. A database itself is a set of tuples carrying records, payload, and metadata, unique ID, and index attribute. A query is simply a predicate over the index attribute. Evaluating a database means returning all matching records. Now we can define the protocols. There are two: setup once and query each query. Conceptually simple, in setup the user starts with a plaintext database and server produces a certain auxiliary structure DS. In query, the user starts with the query, the server uses its structure, and the user is left with the result of the query. Note also that the parties are very stateful. For the sake of completeness, we define the correctness. Simply put, the result of a query needs to be correct for all kinds of databases and queries with overwhelming probability. Reference to probability needed to allow randomized algorithms. Some background on differential privacy here. First, we define differential privacy for an algorithm that is run on a database. We say that the algorithm is differentially private if the output distribution is similar on two neighboring databases that differ in one and only one record. Similarity is precisely mathematically defined with epsilon and delta. One may wonder, how do we add noise to the answer in a way that preserves differential privacy? The simplest method, the one we will use, is the Laplace perturbation algorithm. Depending on the query sensitivity, which are known for the queries that we target, one needs to add a sample of zero mean Laplace with a scale that is sensitivity over the privacy budget. Finally, we'll make use of differentially private sanitizers. Sanitizer is a pair of algorithms with couple properties. Algorithm A is differentially private by itself, and that A can output certain auxiliary structure DS such that the counterpart algorithm B will use it to answer a query with a result that is alpha close to the real one. The sanitizers for different queries exist. For the queries we target, point and range queries, and for the pure and approximate differential privacy, we show the values of alpha. We are particularly interested in the pure differential privacy for our solution. Essentially, value of alpha is the overhead that the sanitizer adds. Finally, we'll use the composition theorem a couple times that tells us the composite privacy budget after running differentially private algorithm over sets. The takeaway is it's the sum of budgets for non-disjoint sets and max of budgets for disjoint. The final prerequisite is the plain old ORM. The access pattern is a sequence of accesses that shows in order to which location the accesses were made, whether the read or write occurred, and what data were written, if any. ORAM, as implied by name, conceals this pattern. ORAM is first and foremost a protocol between stateful parties. The security is defined for sequences of the same lengths, and we say that the ORAM is secure if the adversary cannot distinguish the patterns by observing the server. ORAM protection comes at a cost, but relatively efficient constructions exist. We will use PathORAM with its logarithmic overhead. In this section, we will describe our contributions. We will explain the updated model and the single-threaded and parallel constructions that are secure in this model. Let me introduce the differentially private outsourced system. We essentially require the views of the adversary in the outsourced model to be similar as defined by differential privacy. In human terms, the definition is saying that the protocol is CDP-ODB if the views of the server as seen by the adversary over the execution of the protocols over two neighboring databases are themselves epsilon delta differentially private indistinguishable, except with negligible probability that is needed to account for the computational part of definition. Observe a few properties of this definition. Well, first of all, the entire view of the adversary is DP protected. Second, security in this setting actually implies protection against communication volume and access pattern leakages. In other words, if access pattern or communication volume leaks, one can use it to break our definition. Query sequence is static in the sense that the adversary cannot pick the queries based on data. That is an important limitation, and we will next explain why this is inherent. Let me illustrate the impossibility of data-dependent queries by the example. Let's say we have a medical database with the patients and their diagnosis. Suppose that the typical query flow is like this. First, we query for all patients with the Alzheimer's disease. If there are some, and since the condition is predominantly present in patients of older age, one will query the senior population first for whatever their medical reasons, otherwise proceed normally and query everyone. Observe also that these two outcomes result in a very large difference in the result size. Now imagine if an adversary knows these guidelines. She can then understand the answer to the first query by observing the result size of the second, and this will break the definition. Now we present a construction that satisfies the definition. We call it Epsolute. In the setup, the user has a database and creates an inverted index on it. It then uses the sanitizer to generate that auxiliary structure we were talking about, DS, and sends it to the server. Then the parties use ORAM to securely store the records. In the query, the user first determines the necessary record ID locations from the index locally. It then queries the server's DS to know how many records in total to fetch. It pads its request list with dummy IDs to match that number. And finally, parties engage in ORAM. User gets all the records plus some noise and filters out this noise locally. We prove this construction secure and describe it formally in the paper. Well, we have yet to fill the sanitizers we want to use in the construction. For point queries, we use the aforementioned LPA method and a histogram of a range. We put a sample in each bin, and we need to set alpha, that sanitizer's alpha value, to a certain smallest value, such that we never get a negative Laplace sample. We can derive this optimally, algebraically. Here is the value. Range queries are a bit more complex. We use aggregate tree method, which builds a k-array tree over domain. It places samples in leaves like in the histogram method, but then it puts sample plus the sum of children in the non-leaf nodes. And to use that sanitizer, one needs to find the best range cover for the given query, and then sum up the values in those nodes. As before, we need to fine-tune the alpha, and we do that algebraically again. We have analyzed the construction and present its storage and communication efficiency. We define efficiency roughly as how much the real value is bigger than the ideal. For storage, for example, it's plain text database size versus the server storage. For communication, it's the size of the non-noisy unencrypted records versus what actually gets transferred. From this table, please note pure differential privacy, and note that the ORM adds both additive and multiplicative overhead of logarithm of data size, and the sanitizer adds another logarithm of domain size to the additive term. Epsolute also supports multiple index attributes. One could simply duplicate the absolute instance per attribute, but it would be inefficient. Instead, we observe that we can use the same ORM storage and have to only duplicate teeny tiny index and DS. We also need to use composition theorem and split privacy budget among attributes. We go level higher and present parallel absolute. The idea is to split the states among MRMs, and from here on we will abuse the term RM a little and we will call the respective server storage as RM. Then we need to partition records by their hash of ID and generate M indexes. There is a choice of how to handle DS, and we propose two methods. We generate DS per RM. We will need to take the worst privacy budget according to the composition theorem. We cannot assume that the records will spread uniformly, so we add even more fake records. We then bound this increase to the probability of failure beta. We can do so analytically. Alternative way is to use shared DS. In this case, we add another term to the number of records to fetch, but the K0 term is now smaller, and this method is actually better for larger data sizes, as we will see later. We have analyzed efficiencies of the parallel version as well. Formulas may look complex, but observe that the Y method does not even have the additive term. Here is the schematic representation of the parallel absolute. First, the external application supplies the query to the client party. The client fetches the true record IDs from the indices it has locally. The client then fetches the total number of records to return from DS. It can do so from the server. It then prepares the request to the ORMs and executes them in parallel. That's important. And the results are then filtered out on the client. In this diagram, you can see one of our optimizations. We deploy lightweight machines that only execute ORM against untrusted storage, instead of having a single client machine handle all connections. In this final section, we will talk about the experimental evaluation. We will start with the setup and will then answer 5 questions about the performance of Epsolute. We implemented the construction in C++. We ran the distributed system on GCP using 1 client VM, 8 storage servers, and 8 ORM servers for the default setting. We used 3 datasets that represent salaries. For the default setting, we set the epsilon and beta to standard in the literature values, and we used a uniform dataset with 1 million 4 kilobyte records. The query set has sensitivity of 0.5%, meaning that the query targets 0.5% of the data, and we use shared DS method. We also compared Epsolute against relevant solutions. We use standard RDBMS, Postgres, and MySQL configured for no security and maximum performance. And then we coded up the linear scan solution, which simply downloads everything every time in parallel and answers the query locally. Finally, we obtained shrink-wrap code from the authors and implemented a prototype that only answers range queries and is compatible with our setting. The first question we ask is how Epsolute fares against others. It actually fares well. It is only 4 to 8 times slower than the regular DBMS, but is times and orders of magnitude faster than the scan and shrink wrap. We ran linear scan separately in different settings and observed that it lags Epsolute already at only 10,000 records. Shrink wrap appears slower because it uses linear scan while running in the garbled circuit mode, and it fully pads the result. In this table, we put the observed storage occupied by different components. The bold is server storage, the rest is client. If we look closely at the three highlighted blocks, which represent smallest, default, and biggest data sizes, we will observe that the server to client ratio goes from as small as 85 to as large as over 2000. Some of our observations are the index size expectedly grows only with the data size. DS is negligibly small in practice. Small index and DS sizes imply the efficiency of supporting multiple index attributes, and one can trade client storage for RAM failure probability. We then conclude that the storage requirements of Epsolute are practical. This question is about tuning the Epsolute itself. More experiments are in the paper, but here we will note some observations. Selectivity and record size are linearly correlated with the overhead. Data size is correlated logarithmically due to the use of RAM. Privacy budget epsilon is correlated exponentially, as is clear from the differential privacy definition. How scalable is parallel Epsolute? It actually is pretty scalable. For the shared DS method, the system scales linearly with the number of ORMs. We observe that the shared DS is consistently better. 96 threads is a GCP-related deployment anomaly. 2 ORMs had to share a server. Finally, how well does Epsolute support multiple attributes? We generated 2 attributes with different domains and ran queries against only A, only B, and against both attributes in alternating fashion. We split the budget in half as per composition theorem, and as you may see, the overhead increased only slightly due to a lower privacy budget. Thank you for being with me today. I will now accept any questions.